When we are presented with a material such as tartaric acid and we wish to perform XPS on this material, the information about tartaric acid that we believe to be the case can give us prior warning of what ought to appear in an XPS spectrum, for example the carbon 1s spectrum. We ought to see, if we believe this chemistry to be correct, two peaks. And I say two peaks because there are 4 carbon atoms, but I can identify 2 distinct states in which the carbon exists. There's a carbon that's double bonded to oxygen and single bonded to oxygen, and that is repeated over here. And then we also have another arrangement for carbon and oxygen where carbon is singly bonded to oxygen, and that is repeated a second time. So while we have 4 carbon atoms, there are only 2 carbon chemical states. So we ought to see 2 peaks of equal intensity. Now when we measure tartaric acid by XPS, we end up with a spectrum that almost relates to what we saw, in the sense that we can identify 2 chemically distinct forms of carbon, and they are not quite in the proportion 1:1. There could be explanations for that. We also see structures that are unrelated to carbon bonded to oxygen. So somehow the material that has been measured is not pure tartaric acid. Or perhaps the measurement itself is problematic, in the sense that a peak appears here that is a consequence of differential charging. This is one possibility that we must eliminate before we try to do any chemical state analysis. But on the basis of what we see here, we might conclude that we've got tartaric acid plus some contamination. While a low binding energy peak, such as the one we see here, could be explained by CH-type chemistry from adventitious carbon, there is also the possibility that the sample itself is susceptible to changes under the influence of X-rays. And so a measurement has been performed here where the same 2 spectra, carbon 1s and oxygen 1s, are repeatedly measured, and we can then trace through this sequence to see if there are any changes that are occurring to the data as a consequence of simply measuring by XPS. And as we go down this list, you can see after a while that there is clear evidence that the material does change. So XPS alone is capable of altering the chemistry of tartaric acid. It's also possible any other sample preparation may similarly damage the sample, and what we see here could be just a natural consequence of when we try to prepare a sample for analysis, we don't see the pure tartaric acid simply because we've done something that has changed the original chemistry unintentionally. Before attempting to work out chemical state using a peak model, we ought to make sure that we're comfortable that this is a real peak and not some artifact. And we can do that with this type of measurement, because if we look at, say, the first 5 measurements and overlay these data, well, you can see there's not much change in the shape. There's a slight alteration to some extent, but the nature of this feature that we see at low binding energy, it seems to be consistent. And this is borne out if we look at the oxygen 1s. So the oxygen 1s, again, a well formed peak shape, and there's no obvious extension toward the lower binding energy of signal. So on this basis you might think that there's no real concern for charge compensation for these data. So over 5 measurements it does seem that charge compensation is relatively stable. However, if we now look at another set of oxygen 1s and overlay these, now we see the second set has shifted to higher binding energy, and stepping to the carbon there's a similar sort of shift. So while the charge compensation locally seems to be quite stable, over a period of time there does seem to be some type of evolution. But nevertheless the peak shapes are reasonably stable, they certainly look well formed, so we would not expect charge compensation to have a major influence other than a peak model would have to shift in position to accommodate changes in the spectra in this sequence of measurements. The offsets between these two groups of spectra are related to the initial phase of this measurement. If I start stepping down the spectra, then a point is reached at which the alignment seems to be very good. The shapes are changing, but the alignment of the peaks that we can see seem to be quite good. And if we step over to the oxygen 1s, despite there being some difference in oxygen intensity, for example, the shape of the peaks look reasonably consistent, and also suggest that the shapes that we're seeing here are genuine evolution in chemistry rather than some kind of artifact. Having identified these spectra that are well aligned, I'm going to copy these into a new file, and I'll take the carbon and the oxygen together. So I want to select these two ranges using a combination of shift and control that will produce a selection for both the carbon and the oxygen. I'm going to create a new VAMAS file that's empty and then copy the data as selected. So now I've got a new file that contains the spectra that I thought were of interest, and certainly of interest to me in terms of producing a peak model that might give some information about what we see in this carbon 1s. Before I create a peak model, I'm going to illustrate a couple of features that I will then use later in the creation of the peak model that help me to manage data. Now, if I was interested in performing a fit, say, between the carbon peaks and also potentially introduce some information from the oxygen 1s, then I might want to have a single peak model that applies to both carbon and oxygen. And I can create a VAMAS file that will give me the ability to produce peak models of that nature if I use a toolbar button to select the data from the right hand side on a row by row basis for display in the scroll list. So I have the oxygen and the carbon in each one of these display tiles that is based on the row VAMAS blocks selected in the right hand side. So when I have this format where I've got the scroll list populated with overlaid spectra on a row by row basis, then on the test data property page of the spectrum processing dialog window there's a button that says merge irregular, and when I press this button a new VAMAS file is created, and within the VAMAS file I have spectra that are now merged into VAMAS blocks on the basis of the display tiles in the previous file. And since I have oxygen and carbon in the same VAMAS block, it means that I can construct a peak model that will span both of these photoemission peaks. While creating peak models that involve oxygen and carbon are very useful and can allow constraints to be applied between oxygen and carbon peaks, that's not what I'm going to use this option for, this merge irregular. In this instance, rather than using merge data from different photoemission peaks, if I go back to the file that contained the spectra of interest, I'm going to create a new file that is based on not row by row display of data, but column by column display of data. So I've selected the carbon 1s and the oxygen 1s. I can use this button on the Sims toolbar to overlay columns. So now I've got two display tiles in this scroll list. One contains the carbon 1s, the other contains the oxygen 1s. This now permits the use of this merge irregular, where rather than creating the merger of oxygen and carbon, it merges the individual carbon into a single spectrum and the oxygen into an individual spectrum. And we can see the variation within the data by how variable the plot is of this overlaid spectrum. And the reason this is a reasonable thing to do is it gives you a data file and a VAMAS block, in this case for the carbon 1s, that can be used to fit components to the data in an average sense based on a nonlinear least squares fit. So rather than having a peak model that will fit individual spectra, this will now create a peak model that fits no spectra in particular, but what it does do, it will allow you to fit components with the common full width half maximum and position that is dictated by these merged spectra, that the average spectrum is the target of a least squares fit when we merge data in this form. To illustrate how a peak model might be applied to data such as these, I'm going to produce a relatively unsophisticated peak model. I'm going to assume there are just 3 peaks. This is probably not the case, but nevertheless that's what I'm going to do for illustrative purposes. So first I create a background, and the background provides a basis for placing 3 peaks. So I will create one, just move this over here, 2 and 3 peaks. Let me just adjust the line shapes. I'll just use 3 different line shapes for the sake of argument. And LA 80. So these are just void functions I've used. The names that have been assigned are a little bit excessive, so I'm going to just say C1SA, and let me just transfer that name over to make life easier as I edit these, and C. So I've now got 3 components, and I would like to fit these 3 components without any constraints whatsoever to the data we see here. Let me first of all check what the background looks like. So I would like to move the background a little bit away from the data, and this will give room for void type line shapes. And then let's fit using a chi-square and say fit components. Now we have a fit to these data, and you can see from the residual that the residual has not produced a good fit, in the sense it's not showing a value or a uniformity that you'd expect for a fit to pulse counted data. And that's because these are all data bins with multiple values associated with them. For every spectrum that I had in the original file, I now have that many points for each data bin, and these are all being used to fit a curve in a least squares sense. So the 3 components we see here do not fit any particular spectrum in terms of intensity, but what they do provide is a uniform full width half maximum and position for each one of these components based on fitting to all the data simultaneously. So this is an alternative way of calculating the most appropriate full width half maximum and position for a set of components based on spectra that are all well aligned and are suitable for this type of analysis. So we end up with a set of full width half maxima we see over here, and a set of binding energies that give us some idea about what we should expect if we want to fit these data with 3 peaks.